everyone, thanks for joining today's session, especially at the end of the day. My name is Margaret Schmitt. For those of you who know me, I've been part of semiconductor innovation for the last 25 years in advanced computing, 5G, and mobility. And if you were to ask me what is the most critical problem to address for semiconductor designers today, it's hardware security. And in my presentation today, I'd like to walk you through some insights into hardware attacks, how our current solutions are coping, and share with you an advanced forward-looking approach that'll help us accelerate silicon security. And I'd like to start off by looking at the types of hardware attacks that we've seen. We're seeing a growing sophistication in hardware attacks, from hardware on hardware, software on hardware, and very sophisticated combinations of software, firmware, and hardware exploits. And it's not just the sophistication of these attacks which is growing. It's the impact severity or blast radius from these attacks that's growing and taking on a global scale. And no industry is immune from these attacks. As you can see here, take a look at some of these growth rates of cyber attacks across industries. Don't stand there. The growing rate of cyber attacks across industries where security, reliability, safety, patient health, and data privacy are paramount. And at the center of all of these systems is the chip, the SoCs that are growing in complexity, that are pervasive throughout these designs, with the exploding number of devices in these systems. And the trend for cyber attacks to now be spreading to the semiconductor attack surface is truly alarming, because hardware is a high-value target for attackers. Unlike software that can be patched, the cost and the possibility to replace compromised hardware, of course, can be virtually impossible. But just take a look at some of the costs. $5.6 billion to replace compromised or 5G equipment that's been deemed compromised by the US government. But think of space applications, applications where these systems are deployed for 5, 7, 10 years. So certainly, this is a concerning trend, a clear and present danger, and bad actors, especially state-owned entities, have the ability and resources to conduct these hardware attacks. But there's good news. Problem awareness is growing with our government leadership. Now here, we see here the House language, the report from the House language for the National Defense Authorization Act, from our security leadership, and from our defense leadership here with the NSA and DoD. And these are just a few examples from the US, but also from Europe, from the European Cyber Resilience Act, and from the automotive industry with ISO 21434. So we're okay, right? There's awareness of the problem is growing. There's recognition that hardware assurance and silicon security is important, and it's being recognized by leadership in government, security, defense, and the industry. So let's take a look. How well are we coping and keeping pace with attacks today? So I'd like to share with you the following graph, and this is taken directly from the National Vulnerability Database. So I apologize for the quality. It's a cut and paste. But if we look here, especially since 2017, we can see that the speed of attacks, the speed of the attack sophistication is outpacing our defenses today. Our tools are not only not able to stop new attacks from happening, but it's not able to slow down the trend. A few data points I've extracted from this. We're seeing double the amount of vulnerabilities since 2018, and 2024 is already on pace to be another record year. It's already outpaced 2023 at the same time last year. So we are losing this war. Despite our best attempts to provide secure electronics for our critical systems, we're being outpaced by attacks. So let's take a look at what we in an industry can do in order to have a step ahead. And to do that, let's start to look at the technology we have available today. Now, our conventional security methods are largely forensic in nature. We're looking at known hardware attacks. Our understanding based on the history of how these attacks have happened in the past. So we identify an attack, we hand code rules and guidelines to ensure that that attack does not happen in the future. There's 3 limitations to this approach. 1, it requires someone to analyze the attack and hard code rules in order to detect that attack going forward. Now, this can happen at the vendor with hard-coded rules into the tools or products. This can happen in the design house with actually targeted rules for a specific design type. Limitation, of course, this is time-consuming, resource-intensive, and requires an expertise in security, architecture, and design that may be not available or very limited. Second limitation, even if I'm writing rules and covering the attacks of last year, you saw from that increase in that vulnerability database, we're seeing more and more attacks in the following years. And my semiconductor device is going to be deployed for the next 5 years, and I'll be exposed to those upcoming attacks. And third of all, these solutions aren't scalable to large designs. So at any one time, I'm only able to see a small snapshot of the security level of my device. So essentially, we're playing a very high stakes game of whack-a-mole for security. We see an attack, we write a rule. We see another attack, we write a rule. Well, anyone who's played whack-a-mole knows how frustrating that is. We're taking a reactive stance, and now we have an opportunity to take a predictive, proactive stance to get ahead of our attackers. So at Amida, we've taken a different approach. We look at the comprehensive semiconductor attack surface, and we analyze this to understand, 1, how could attackers attack this design? Where are the design weaknesses, and what forms would that attack take? And what would be the impact? What is the impact severity? How critical is that security issue? And the advantages of this approach is that it's deductive. We're not starting with a hard-coded rule. We're starting with the attack objectives in mind. And with those attack objectives, we can scan the chip attack surface and understand where could data be leaked for this design? Where could a denial of service attack be launched? Where could someone take control of this design? And because we're analyzing this starting from the RTL, it's actually a very automated approach, and it doesn't require expertise. Excuse me. Gentlemen, may I ask for a cup of water? Apologies. Thank you. Pardon me, folks, bad allergies. And I'll double click on the automated analysis for just a second. We've developed a unique graph transformation based on the RTL that lets us traverse through the design and understand the relationships of the data and the data flow, as well as the data and control states throughout the design, to let us identify where these weaknesses and vulnerabilities would be. So we're taking the burden off the designer to design rules, to hard code checks, and let them perform this analysis automatically. And of course, it's predictive in nature, allowing us to identify various types of attacks throughout the design. And thanks to it being automated based on RTL, thank you very much. Thanks to it being based on the RTL, of course, it's scalable to larger designs. Pardon me, folks. Truly apologize. California native, and I have a lot of allergies. Now, what is the advantage of this approach? Well, the advantage is we can identify weaknesses in the designs which will be missed by forensic methods. Missed by forensic methods because you didn't define a security rule, or you missed a design element, or you weren't able to predict a future attack vector, or you weren't able to run your complete design due to the limitations of your tool. Now, of course, this means instead of looking at the 100 issues that failed in the past, you're now potentially looking at 1,000 issues that could fail in the future. It can be daunting. We've been analyzing designs, and when you're seeing your first full pictures of full chip vulnerabilities, it can certainly be a bit scary. But we help you prioritize. We identify those critical areas where attention is needed to improve your chip security. We prioritize those based on a quantitative assessment, based on impact severity, based on type. And then, of course, designers can take the next steps to mitigate that risk in their RTL, and or understand the acceptable residual risk in their design, as well as identify critical assets that they may need to monitor on an ongoing and continuous basis. And I'll talk about system monitoring more in a minute. So now we have a predictive approach to scanning the chip surface, identifying design vulnerabilities that could potentially be exploited, and designers can take the next steps to redefine or refactor their logic, take this information back to their security architecture and ensure that they're going to have robust protection as their designs evolve against future threats. But the security posture should not just stop there. It should not just stop with hardware fab out. We can extend our security posture to the entire life cycle of the chip. So how can we do that? Well, now that we've got an idea, we've got a scan, a security scan of the chip surface, understanding where the vulnerabilities are located, we can use this to guide on-chip instrumentation, on-chip instrumentation that we can use for further attack emulation, that we can use for in-system monitoring and intrusion detection in actual deployment and operation of that design. And the key to implementing that, of course, is an AI/ML-based solution that I'm going to talk about in more detail. But to tie this together to an analogy that I often think of, a security posture is like a museum. The doors, the windows, the ceiling, these are covered by the forensic approach. These are known attack angles. Someone's broken in that way before. But history has proven that attackers will find new ways to break into that museum. So with vulnerability analysis, we're essentially identifying your critical key assets in your design, your area of weaknesses. And now, with system monitoring, we're going to take the next step and we're going to put tripwires throughout that museum, tripwires throughout that design, that in the event of an intrusion, that tripwire is going to flip and we're going to detect a design. Now, the key to that, of course, is an ML machine learning based model. Very careful there, machine learning. And in order to have a machine learning model that's going to enable us to create a golden model of the design versus a design that's under attack, let's call it the device under attack, we need two things. We need visibility into the chip attack surface, not just the interfaces, not just the readily available states, but we need the states that are critical for monitoring and collecting data and training our model for security. So that's going to be key. And we don't have that by default. Then we need a sufficient number of training vectors that we're going to be able to use to run our golden model, compare our device under attack so that we can detect anomalies in the system. So these are two key important pieces of data that we need to have in order to build our model. And our vulnerability analysis that we've run will help us complete that equation. Based on our vulnerability analysis, we have the graph transform of the chip attack surface. So we have exposure of the states of the design, but we can't instrument every state. That's not practical, that's not possible. We want to have instrumentation of the design that lets us monitor the key areas of security without overburdening us with instrumentation, power, cost, what have you. Thanks to the vulnerability analysis in our security scan, we highlight those key areas and those states which are critical for monitoring for security, and this can help us guide our instrumentation into the next step to build that machine learning model. And so now we have the device level instrumentation that will let us build a golden device model, and now we build the device under attack. And we do that by injecting Trojans with different various types of attack. And the Trojan in this case is the perfect stand-in for a successful penetration of our first layer of security. So we'll do this with various forms of Trojans to represent various attacks, so we'll be able to detect those. So what this gives us is a holistic approach, end-to-end, of a framework that lets us not only identify vulnerabilities in the design, it helps us drive instrumentation, that helps us train a machine learning model that can create a golden device, a device under attack. Based on this information, we can inject Trojans that will help us identify these intrusions and raise an alarm, raise that tripwire in a system-level deployment. But this framework also lets us optimize, it's actually an iterative process, lets us optimize the performance and metrics, but it can also continue to learn, and that's key. Because of course, we're talking about future attack vectors. So as we identify these, we can continue to train the machine learning models to make the system more robust. So how do we deploy an end-to-end holistic predictive analysis that starts with silicon and extends through to the system? So breaking this down, we started with an RTL vulnerability analysis. And that analysis goes beyond forensic methods, goes beyond formal methods to detect design vulnerabilities on the chip attack surface. And it enables designers to understand the risk of those vulnerabilities to the design. Now, of course, will there ever be a design without risk, without vulnerabilities? With the current state, no. But we as designers can use this information to understand our security coverage, to understand our risk, and to focus on those key areas of the design that we need to bring under control into an acceptable risk. And that's actually something that we'll iterate on over time, focusing first on the critical vulnerabilities, understanding the residual risk, iterating over time to reduce the risk and bring our entire design within an acceptable security threshold. We can then take that design and we can use that information to guide a system-level monitoring in-field detection, and the key to that is instrumentation that is optimized and determined by the vulnerabilities found from this flow. So the key to successful semiconductor and silicon security will not only be a flow that is easy, again, to deploy, to use, to manage, but of course helps design organization manage the cost, the resources, and the talent they need in order to make their designs cyber resilient for today's critical systems. And I'd like to wrap up my presentation portion and leave you with a thought. As we saw from the vulnerabilities database, attackers are changing up their strategy and the character of hardware attacks. And now for this community, focused on creating secure silicon, focused on meeting this challenge, we have to not just react to these attackers, but we need to take a predictive approach that helps us cyber harden our design against future threats. And this, I truly believe this is the semiconductor forum to discuss these topics. And I look forward, I intentionally left 10 minutes so we could have some questions. And I look forward to those. And I certainly thank you all for your attention at the end of the day. Yeah. I've been told these mics are live. And we got a couple of minutes. So any questions, happy to take those.
Hi, I think it's really neat that you're able to take an RTL and do a vulnerability analysis and generate these auto checks as well as create these monitors.
I'm so sorry, sir. I'm having a hard time. Can we maybe get some technical, is it me? Am I doing something? Okay.
Okay, can you hear me?
Great.
Okay. Yeah, I said it's really impressive that you're able to take an RTL, which is what most of the designers work with, do some analysis, a vulnerability analysis, and generate those auto checks, as well as generate those monitors. Can you give me an example of a couple of vulnerability checks that are generated by your tool, as well as the monitors, to give us, this is at a very 20,000 feet view. I'm looking for like a specific check that would be generated or a monitor that would be generated.
Absolutely. I'd love to show, as a matter of fact, I can even do one step further. We actually brought a live demo of our tool, this predictive analysis, here to DAC, and we've prepared some results on an open source RISC-V processor. So if you'd like to come by and take a look at those, I'll just make a quick announcement. Please come by and see that. But essentially, what we've implemented right now is a first step. We're looking at things like data integrity, data leakage. So we're able to identify areas where data could be leaked from the design, exfiltrated from the design. We also focused on denial of service attacks. So we can identify areas in the design that potentially would have would be exploitable, would have both the influence and the exposure, so to say, to highlight that. These are a few of the checks. I can kind of go down the list. We focused on a certain set now, and we're certainly welcoming input from the industry, what we should continue to prioritize and build on. What I can foresee if I were a user is wanting to own this. I kind of jokingly talked about, the whack-a-mole and writing rules. And I'm thinking that how can we make that easy, scalable for designers, and potentially different types of design may want to have customized rules. And how do we enable that in a flexible environment? Not to mention LLMs, right? Yes, no, but to answer your question quite seriously, we have focused on those areas that I described earlier: denial of service, data integrity, and reliability and behavior. Why did we focus on those? Because those were the ones that we were directing toward critical infrastructure and aerospace and defense types of applications. Now, of course, on the automotive side, you have additional care abouts. Each industry is going to be slightly different. But the health example, data exfiltration, these types of things. So we definitely look forward to expanding that. The RTL analysis is available today. We're demoing it in the booth, so certainly invited to stop by and look at that. And that is the tool we're evaluating with customers today. So yes, we're actively working. Yeah. No, thank you. I apologize for the audio challenges. Yeah, thank you so much. Folks, we still have time for some questions.
What about side channels? Side channels, stuff that's not visible in detail?
Oh, yeah, I'm so sorry, thank you. Great question. Now, side channels, of course, if you're looking at dynamic side channels, those are fluctuations in, related to power. That's a dynamic analysis type of focus. What we're talking about today is based on the RTL. It's more of an information flow data flow framework. However, that is a framework that could be used as a base to add that type of information in, annotate that information to look to that. So that would be a forward-looking application for this. This would be a first framework to detect those vulnerabilities that we were just discussing. And I'm very aware that in side channel attacks, there's a number of solutions out there. There's a number of people looking at that problem. So I'm confident there's going to be some good solutions out there. The question is, what's the most efficient way to bring this to designers so there's not a lot of overhead, resource, as we discussed earlier, being able to get to that solution quickly and efficiently. And accurately, of course. Yeah, good question. Okay, 3 more minutes.
So in your sorry, can you hear me? Yeah. So in the flow, you need to inject some thought in the golden model, right? So I have 2 questions. First, where does that golden model come from? And then second, does that mean we only handle those known issues? Like if there's because you need to inject certain pattern, how well it is to detect those unknown issues?
Okay, I think I got the first part.
Okay, yeah.
Where does the gold model come from?
Yes, that is
okay,
the first
so
question.
where the gold come from? This is the chip under normal operation. So you're talking about really running through various states of that chip, your regular functional vectors, for example, on the hardened design. Because if you're running, of course, a golden model and that model hasn't been run through the analysis, you're potentially creating a golden model that actually is containing vulnerabilities. So we want to make sure we're cyber hardening that design first so we know that those vulnerabilities have been addressed and then leveraging that golden model.
But that assumes the design itself is perfect. There's no unknown issues with that golden model.
Not perfect, not perfect.
Yeah.
Are we ever going to have a design that has no vulnerabilities? Probably not in I won't say my lifetime, but my career lifetime. But it's very as I was highlighting earlier, to understand what is your risk, what is your acceptable risk. Different processors may have different care-abouts. Maybe you don't care about this type of attack, but you do care about another. So the assumption is for that golden model, you've addressed and brought your security assessment to your acceptable threshold as a starting point.
Okay, yeah, so thanks for that. And my second question is after you have the golden model, you need to inject some error, or inject some attack, right, and to get the training data. But in that case, assume that the attack inject is all unknown issues, or attacks that people are already aware of. So with that training data, how aware it is to detect those unknown issues?
Yeah, that's a really great question, and I didn't double click on that in this presentation. But of course, the way I presented it was, okay, we're injecting Trojans of known attacks, and I kind of almost made it look like a static process, but it really isn't. And there's quite a lot of research going on in the community, and a number of people in the audience involved in that, where you can take a look at what generative AI and LLM can do in the area of Trojans. It's a very, very exciting field. There's a lot of really great work done on it, and essentially, this may, since we've got a minute, if you actually open up an LLM, open up ChatGPT 4.0, for example, and ask it to write a Trojan for you or ask it to exploit a hardware vulnerability, it'll do that right on demand. So how can we look to evolve that? I want to call it a Trojan library, but on the other side, I don't want to call it a Trojan library because Trojan libraries are static, and this is an evolving type of nature. So I absolutely see a capability to, again, very similar to the question, start with a focused set of attacks, focused set of Trojans, but I absolutely see new technologies out there that's going to help us scale to these, learn more unknown attacks. Yeah, I think that's the future. There's great insight. Hey, folks, we got 1 minute left. Of course, I should remember it's also probably 5 o'clock. Thank you all for hanging in there with me, and really excited to bring this topic.
Since no one else has asked.
Okay, sweet. Let's have it.
So you mentioned about monitors. So these monitors, are these SVM monitors? What's the nature of these monitors that you generate?
Yeah, okay, another really great question. Very forward thinking. Okay, here's the story. We talked about various types of attack. Well, it's quite possible that a certain design weakness vulnerability may be susceptible to multiple types of attacks. Well, then you might need different sets of monitors there. So we're not just talking about one static monitor that's toggle counter or something. I just made that up, but you actually have to take the vulnerability analysis, understand what type of vulnerability still exists, and make sure the monitor is assigned for that. And of course, that's something that we're developing to be automatic for you. You're not going to have to go do that by hand. Don't worry. Yeah. Great forward-looking question, though. Yeah. Thank you all. Appreciate it. Have a great DAC, and look forward to questions going forward. Thank you.